Welcome to Science and Technology in Business. Subscribe our channel to get more videos about science and technology in business. That's a fantastic area to focus on, as qubit fidelity and scale represent the two major hurdles that must be overcome to achieve truly useful, fault-tolerant quantum computing. Here is a breakdown of the latest progress and the innovative approaches researchers are taking to tackle this dual challenge. The state of qubit scale and platforms. The field is characterized by intense competition across several different hardware platforms, each having a unique strength in either scale or fidelity. There are two major points. Point 1 is the race for qubit count, scale, and point 2 is the fight for fidelity, low error rate. Let's discuss point 1 first. The point 1 is the race for qubit count. While high qubit counts don't guarantee immediate computational advantage due to errors, they demonstrate significant engineering progress in scaling up the hardware. Neutral atoms. This platform has shown the most dramatic scaling recently. Breakthrough. Researchers have announced systems containing arrays with over 6,100 neutral atoms, qubits. These systems operate using highly excited electronic states, Rydberg atoms, and are a major contender for large-scale, room-temperature operations. Superconducting qubits, IBM, Google. These platforms currently lead in commercial availability and circuit depth. Point 2 current hardware. Companies are pushing past the 100-qubit mark, with processors like Google's Willow, 105-qubit, and IBM's Condor, 121-qubit. Being examples of current high-count systems. Point 3, the focus here is on integrating these chips into modular, networked architectures. Photonic qubits, Xanadu, focused on networkability. These systems can operate at room temperature. Point 4 architecture. Xanadu announced Aurora, a networked and modular photonic quantum computer featuring 35 photonic chips and $5.13/TaxChem of fiber optics to achieve a 12-qubit system that prioritizes scalability and modularity. Point 6. Let's go for second point. The point 2 is the fight for fidelity. Fidelity refers to the accuracy of quantum operations, gates. Achieving high fidelity is paramount because errors compound rapidly in quantum algorithms. The target is to get below the quantum error correction threshold, often cited as an error rate below 1% to 0.1% for the physical qubits. Metric record-breaking achievement, platform, error rate context, single qubit gate fidelity, trapped ion, Oxford University, 0.00015%. 1 error per 6.7 million ops, achieved using a trapped calcium ion controlled by electronic, microwave, signals, simplifying complexity. Superconducting qubit fidelity, fluxonium qubit, MIT, 0.002%. 1 error per 50,000 ops. Achieved math BF 99.998%. Single qubit gate fidelity using novel fluxonium qubits, which offer longer coherence times than traditional transmits. 2 qubit gate fidelity superconducting fluxonium, MIT, 0.1%. 1 error per 1,000 ops. This is still the primary bottleneck. 2-qubit gate error rates remain significantly higher, around 1 in 1,000 or 0.1% in the best cases, than single-qubit rates. What is a logical qubit? In a nutshell, a logical qubit is a highly reliable, error-corrected quantum bit that is encoded using a cluster of several less reliable physical qubits. The main distinction is physical qubit, the actual individual quantum hardware, like a trapped ion or superconducting circuit, that is very fragile and prone to errors from its environment, decoherence. Logical qubit, a robust, abstract unit of quantum information that is protected by an error correction scheme. This is the unit that is actually used to run complex quantum algorithms. The role of quantum error correction, QEC. Physical qubits are inherently noisy. To make quantum computation useful, errors must be managed. This is where the logical qubit comes in, acting as an error-corrected qubit through redundancy. Encoding. The quantum state of a single logical qubit is spread across multiple physical qubits. For example, a common goal is to use hundreds or even thousands of physical qubits to encode just one logical qubit. One well-known encoding scheme is the surface code, which arranges qubits in a 2D grid and is a leading candidate for building fault-tolerant quantum computers. Detection and correction. The physical qubits within a logical qubit are constantly monitored using auxiliary ancilla qubits, or measurement qubits, to detect errors without destroying the stored quantum information. If an error is detected in one physical qubit, it can be corrected based on the states of its redundant neighbors, preserving the overall logical state. The goal is to reach a point where the error rate of the logical qubit is significantly lower than that of any of its constituent physical qubits. The scaling challenge, quantum error correction, QEC. The consensus across the industry is that it is impossible to build a useful quantum computer by simply trying to make physical qubits perfect. The solution is fault tolerance, using QEC codes to turn many noisy physical qubits into one reliable logical qubit. Key breakthroughs in error correction logical qubit scaling. Google's work with a surface code architecture has demonstrated a key milestone. They show that the performance of a logical qubit improves, the error rate decreases, as the number of physical qubits encoding it increases, e.g., going from a 3x3 to a 7x7 lattice. This is the first experimental demonstration of exponential error suppression in a logical qubit. The 7x7 logical qubit on their Willow processor lived twice as long as its best physical qubit, proving the QEC principle works. 16 Increase coherence time. Fluxonium and feedback researchers are improving physical qubit performance by new qubit designs, utilizing fluxonium qubits, which inherently have longer coherence times, how long a qubit remains stable, compared to trans-Mon qubits. Active control, employing closed-loop feedback protocols to actively stabilize the frequency fluctuations of superconducting qubits. This process compensates for environmental noise in real time, resulting in improved coherence and gate fidelity. Advanced materials, research into ultra-pure materials, low-loss dielectrics, and new surface treatments is critical to minimizing the environmental noise and defects that cause decoherence in the first place. Subscribe our channel to get more videos about science and technology and business. Subscribe our channel and hit the bell icon to get our video first to you.